My name is Yannic. I work at EnchFlow, but similar to the last talk, I will keep it short because you already know or you just don't care. Today, we will talk a bit about how to design efficient data structures by using list-like data structures like lists and stacks and queues as an example. So first, let's look into what's available in C++ today. I did take these three examples. There's a couple of more in the standard library, but these are the most well-known. There is on one side a vector, then there is the std list, and then there is the deque or deque, whatever you want to pronounce it. It starts with vector. That's the C++ version basically of an array-like data structure. The way it works is you have one single C-style memory area array, which holds the data, and then you have a start pointer and end pointer for the size and the capacity, so you know how much space is in that C-style array, and you can do some bounds checking and stuff like that. And it automatically grows for you. So if you insert something into a vector that's already full, it will allocate a new array for you and copy everything over, and then it will still work. You can implement a bit like this. I already mentioned there's the size, which is the current size of the number of elements, the capacity, which is basically the size of the backing array, and then a pointer to the array itself. And of course, a bunch of constructors, accessors, destructors that automatically freeze the memory, does bounds checks, whatnot. We are all familiar with this, right? The advantages of this is it's a very compact layout. Element is stored in contiguous memory. It's a C-style array after all. Inserting and removing elements at the end is extremely cheap, right? You don't have to do anything. I mean, we might have to copy the array, but you can, it's constant time. And accessing elements in random order is also really cheap. Because you can automatically compute the address of the element, so it's perfectly fine. Inserting and removing elements in any other position is a bit expensive because you get to move everything that comes after. So basically the worst case scenario is you always insert front, and then you have to copy everything all the time. Let's go to list. That is the C++ version of a linked list, often called linked list data structure. There's a couple of variations of this, like singly linked list, doubly linked list, whatnot. For simplicity, we're not going to go into too much detail there. And the essential thing here is that elements are stored in individual nodes, like every element gets its own node in memory. And then that has a pointer basically to the next node, often also to the previous node. To make it a list. In memory, this looks a bit like this. You have the list container itself. Can you see the mouse? Yeah, you can see the mouse. And then that references the first element, which is a node. And then that references a couple of other elements. And a lot of times you also have a pointer to the last, so you can do very cheap insertions at the end of the list as well. But as you can see, if you want to access this element, you have to go to the fourth element. You have to start as if the first element, dereference this, dereference this, dereference this. So this is a bit expensive. And since these are all individually allocated nodes, they happen to be in basically random locations in memory. Consequently, inserting and removing elements at the beginning and at the end of the list is very cheap because we have pointers to that thing and we can just insert another node there. But accessing elements in random order is really expensive because you can only really access the first and the last. And if you want to access anything in between, sorry, the monitor was acting up. You have to basically walk the whole list. Then there is deque, which is conceptually somewhere between those two. It's a table of vectors. That has the benefit that it stores elements in chunks of contiguous memory, so you don't get these individual nodes in memory. Instead, you get something like a vector, and then that reference another vector, and something like that. But as a table, inserting, removing elements at the front and at the beginning, at the beginning and at the end is really cheap because similar to list, we have direct pointers to that. Accessing elements in random order is also reasonably cheap because it's not actually linked lists of memory pages. There is a table that references that. But inserting and removing elements at any other positions is also still as expensive as with the vector or with the linked list because we still might need to copy and move lots of elements around. Now, if you can build a static that basically looks like a list, and then you can get cheaper random access, random insertions and deletions, but you also get this property that we had with the linked list that everything is its own node, basically. Another thing about the deque is that it requires some additional indirection because of the table that it uses to reference elements. And depending on the architecture, that can be a bit expensive. This actually works quite well with the talk that was, with the other talk that was right before, which is the virtualizing functions. Avoiding virtual functions is maybe pointless because it also goes really a bit into the CPU architectures. Now, if we think about CPUs, a lot of times when we design data structures, it looks something like this. We have one or multiple cores, and there is some memory, and we can treat that as, or we tend to treat it as, well, it's random access memory, so we can access random addresses in constant time, and it doesn't matter what we're accessing. But for the past, well, probably decades by now, CPUs actually look a bit closer to this, where every core gets its own cache, its own L1 cache, its own L2 cache. And then there's the L3 cache, which is shared between cores sometimes. Again, this is just a model. If you talk to anyone actually building CPUs, this is probably completely wrong. I'm actually pretty sure this is completely wrong. But as a model, this is sufficient. And if you dig a bit deeper, then even the L1 caches, they are divided into individual cache lines. On most common CPUs, these are actually 64 bytes wide, every cache line. And you get a total of a couple of kilobytes typically. So even there, you get either the full line cached or not cached at all. There's also quite a few strategies for inserting this and how to invalidate the caches. What happens if you have multi-threaded programs and you write to a cache that's also like to a cache line that is shared between that has some values that are shared between other threads, and then you have cache currents and whatnot. We're going to ignore that in this talk, mostly because of time. But there's many things in modern CPUs that the classical data structure architectures just don't take into account. So if we go back to the std list example, one of the bigger problems there was that it stores things into random locations in memory. And that basically means you will not ever get any cache hits from the same line because everything will be in a different cache line. So what if we change the list to be a bit more efficient, and instead of allocating them in completely random locations in memory, we basically put them into pages of memory and make it make it a bit more cache friendly so that we can load one cache line from main memory. And then for the next couple of elements that we have in our list, we can also access that cache line, and it will be nice and fast. You don't have to pay a price to go to main memory all the time. Visualize this would look something like this. We still have the individual nodes holding the elements. We still have just the first and the last pointer. But they are actually aligned into a single line of cache. And that actually also explains why I did put the nodes basically all over the place in the previous one, because I wanted to visualize that this is random memory locations, and this is a bit more controlled memory locations. Now, this as I already said, packing them into nodes of contiguous memory, into chunks of contiguous memory, provides you a slightly better cache locality. But having an individual node for every element is still quite expensive. Like you need to store basically the element itself and 2 pointers. And if your element is super small, like an integer or something, then it's a huge price to pay. You waste a lot of memory. So I took this a bit further and came up with a design that that gets rid of those inefficiencies, because a lot of times you don't have just big elements. Lots of elements are quite small, and you also barely ever have just one element in your list, because why you use a list in the first place? So I came up with a design of that basically packs all the elements into one contiguous chunk of memory and avoids all of these extra pointers. And the simplest version of that is something I call fixed stack, which is an implementation of a stack that just has a compile time size. Conceptually, it's kind of similar like to a std vector, except that it doesn't automatically grow. And it also avoids some heap allocations for small objects. So let's look at some code again. Again, the actual implementation is quite a bit more complicated. But for simplicity, there is a method to add an element. There's a method to get the element. There's, of course, also some methods to get how big, like how many elements are in the stack at that time. And then there is something called page, which is just this container of contiguous memory for a bunch of objects. And again, for small objects, all of this is just inlined. You can put it onto your stack, like actually stack allocated, or even heap allocated if you can. And it will all be on stack. The stack will be on stack. But for larger elements or for larger stacks, it actually you can show with some benchmarks, or at least you can measure with some benchmarks and some profiling, that if your stack grows too big, then it does actually make sense to have that heap allocation and not have it on the local stack, because then you will just, I don't know, have 100 megabytes on your stack. That might not be a good idea. Let's look a bit at page. Page is a container that actually implements both can be implemented to implement both queues and stacks, but also lists. And it has a method to get the front, to get the back, to remove the front, to remove the back, and to also insert the front and insert the back, that I didn't put on the slide, unfortunately. And it tracks which elements it has, like what's the current position on the front of that contiguous memory and at the back of the contiguous memory for inserting or removing, depending on what you want to do. And it has, again, a C-style inlined array of slots. And what does slot look like? Well, for slot, it actually depends. This is what I was saying earlier, that sometimes it does make sense for large objects to not be inlined into the container. The idea behind that is that you want to fit as many elements into your cache line as you can. And if your object happens to be something like 50 bytes, then you're not going to fit much into that. So it can actually make sense and make your program faster, or show that that part of the implementation shows less in profiling. If you don't inline and do pay for that extra memory indirection by storing the element into a separate location in the heap. So this is the version of the inline slot, which it's not too complicated. The actual implementation is a bit more complicated because it needs to deal with a couple of other things that I I'm ignoring for this talk. But it basically just provides a bit of memory that is aligned as the element itself, and then it provides a constructor and an accessor to fill or to remove it, and that's basically it. For the not inline version, I have a typo here because it shouldn't be aligned as T. For the not inline versions, it's exactly what you expect. You have the same object, but it points to another location in memory, and then you can just new the object and delete the object. So this is more of an abstraction, so you can use the same API in both cases. Now we're done with stacks and with the fixed stacks. Let's go a bit further into a queue, and this is actually a version of a queue that can dynamically grow at runtime. That only allows you to add an element in the front and remove one in the back. And it's actually implemented quite similar to the linked list example, except that it has a list of, like every node is a page list, and then you also point to the first and to the last page list. And you always insert at the end, and you always remove from the front, and if there is no more space at the end, you will allocate a new page list and like append it, update the last pointer, and all of that. And if you happen to completely exhaust the first page, like if there's no more elements in the first page, you can remove it and update the first pointer to the next page. When is this useful? Well, this is actually a real example I am using this for, which is a task queue, which is a system where you can you have a bunch of one or multiple threads that run your tasks, and you can insert the tasks into that, and then you can just push one into the task queue, and it will run on one of those dedicated threads. Which can be helpful, for example, if you want to do all I/O on a handful of threads, or all network on a handful of threads, and then in the end call back to another thread. So you get some control. This actually doesn't use queue directly because this needs to be thread safe. I am skipping the details of this thread safe queue here because that is just a bit of synchronization and atomic pointers. There was another talk yesterday about log-free atomic queues that did explain some of these things. I unfortunately couldn't attend this, but there is some other thing at CppCon happening that explains log-free queues and how to make them efficient. So let's look a bit into that, and I'm actually quite good in time, it seems. Let's look a bit at benchmarks. What I haven't mentioned benchmarks before in this talk, mostly because benchmarking this is incredibly complicated. If you try to benchmark, for example, the linked list and the linked list with a custom allocator, if you do it the naive way, it will just be exactly the same, because it turns out it will already be in the cache lines. Like all the nodes will already be in the cache line, because your benchmark is not going to do anything else. It invalidates those cache lines. So measuring this is a bit tricky. I did do some profiling on this that shows that for the task queue, I see a lot less overhead when passing tasks between different threads by scheduling them into the queue. And there is also a lot less synchronization needed with the thread-safe queue than with the deque or the list, because those are inherently not thread-safe. But these are all a bit early results, and there's definitely some more benchmarking that needs to be done before you should really put that into your production system. But I'm confident that we will get there. The other thing that some of you might ask themselves, Oh yeah, as I already said, these are still experimental. And they need some more work to be stabilized. As some of you might already ask themselves, can I use this? Can I play around with this? Unfortunately, not yet. I was planning to open source this before CppCon, but it's part of a larger repository. It has some instrumentation inside the queue, so I can get visibility into what's happening when scheduling these tasks use. And that made open sourcing a bit hard. And I also got sidetracked a lot by other projects. Sorry. But I'm actually pretty close to being done with this, so I expect this to happen in probably November or December. All right, and that's basically already it. If you have any questions, then please come to me, either now or also later. Feel free to talk to me at any time. And yeah, that's it.
Hi, thank you. I have two small questions, I guess. One is you showed you use chart buffer for storing an element. And is there any reason why you did that over a union?
It was slightly easier to implement this way. I had to fight the compiler less.
Cool.
I've done something similar in the past, so I went to this trick immediately. But I remember fighting a bit with a union.
All right. Just so
But I'm sure it's possible to implement with a union.
okay. The second question is, you mentioned a little bit that cache and benchmarks. And I struggled with that recently, and I couldn't make it work, like a good cache invalidation. Can you maybe talk about that? How did you achieve a good cache invalidation?
I didn't. That's what I mentioned in why I didn't show the benchmarks for the custom allocator, for example. I benchmarked this actually by having a bigger program and then doing profiling and checking what the CPU is doing and how much it's in that specific part of the code versus with different queue implementations. And that way you can benchmark it without actually like having a micro benchmark.
All right. No, I think
Another trick could be that you just randomly allocate objects into memory and then free them, use them a bit, free them. But that might have overhead as well.
we try copying a lot, but just hard.
It's just hard to do.
All right.
The CPU doesn't want you to invalidate the cache. Any other questions? All right, I guess that's it. Done. Thank you.